So finicky.
Alrighty. So today I'm gonna be talking about work. So let's see. Let me go ahead and write this down. Now, how can you
is going to equal to what? Minus 1
transfer
half
energy to an object?
E squared over R
So in order
of N. Make sense?
to transfer energy
What's the charge? It's going to be 1.6
to an object,
negative 19 coulomb, right? Your K is going to be what? What's
you
K?
need
which constant?
to
Yeah, exactly.
extend a force on it.
9 times 10 to the 9.
On what? On that
And then
object.
Rn.
In
What's
order to
Rn?
transfer energy to an
Goes up on
object,
the
you
force
need
radius,
to
right?
exert
Which is R1,
a
yeah.
force on that object or
Yeah, for
extent.
R1, hold on.
Just like that.
Rn. For R1,
Yeah.
it's going to be what? 5.7
So a lot of y'all, for
negative
instance,
11,
know that I
right?
travel a
Did
lot.
you get that last time?
And
That means for
you know, I
Rn,
go in and that
it's going to equal to N
me.
squared
And
R1.
let's say this is
Right?
my
N
bag.
squared times
So it's like
5.3.
a little bag that's coming in like this. And I'm actually pulling it in with my hand, and the bag has like a little wheel.
What's your
In order for me
level
to move it, which
Your
I'm going in
difference
that
level is gonna
direction.
be Minus.
Now, in order for me to move it,
So this would be, that's
we've
your
seen this in previous classes.
1.6 times the negative
You're gonna have to
19
exert a force
times,
F on
For the
it.
first one, be 5.3.
Well,
111
let me
divided
go
by 2,
ahead
you get minus
and
3.17,
just draw this F vector right now over here.
negative 18 joules.
Now, this one is a vector, so it consists of your
Which means
fx direction and your fy coordinate direction, which is, this one's gonna equal to, this is your angle theta,
E of N equals minus
so it's gonna
1
equal
half
to your
N
force
squared
F
over N squared R1.
cosine theta. This is gonna be your force F sine theta. Now, your work in this case
Okay, so K E
is
squared
going to be a dot product. This dot product
N1 R1 is going to equal minus 1 half K E squared over R1 N squared.
the dot product
Just put them right, which is this part.
is, when you instance you have a vector dot b
Is what?
is going to equal to
Is this, right?
ab cosine
This is going to equal to E1.
the angle between them, theta. So in this case, what we're doing the dot with is between the force
equals E
and the distance traveled
squared.
that I'm taking this way. I'm going to call it d. And then this is for your distance displacement. And f, that's your force.
Let me go ahead and write it down. E1 equals E1 over
So in this case, your work is your
So-
dot product of
basically Bohr's
the
model.
force multiplied dot
We did this.
distance. So let me go ahead and write this down.
The
The work is your force dot distance,
ionization
which is going to equal to, according to our rule,
energy
your force multiplied by your distance multiplied by cosine the angle between them.
the electron.
So let me go ahead and label this. W is going to be your work, which is your amount of energy,
Alright?
the force is given to an object. Your F, that's your force. I'm going to get another color for this one. You need that displacement while
Alright. So if we wanna calculate,
the force
so
is on it.
square
And your last but not least,
minus 2.7
your theta
times 10 -18 joules, and we said 1 electron volt
is your
10
angle
19 joules, right?
between
So E of 1 is going to equal to what?
the force
Or E of,
and displacement of the object.
actually, before I do anything, let me just convert this
Let me go ahead and just
electron
label
volts, right?
these.
So what you get? 2.17 times 10 -18 joules. You multiply it
Awesome.
by 1 electron volt is 1.6 times 10 -19 joules, right? So that means we want, and
So-
is going to equal to,
The only, let me go ahead and write this down. The only part of the force that does work is the component that lies with the direction
EV.
of the displacement. When I'm moving my bag,
So this
it's going in to the direction of displacement. What if, and that's going towards the x direction with an angle of theta. What if I was going towards the y direction?
one,
Well, your cosine theta is going to equal to,
51 was minus
let
6.
me go ahead and write it down. Your cosine theta will equal to,
That means E of n is going to equal to what?
if you go in the x direction, cosine 90 degrees is going to equal to
You see that?
0. That's if you go in the y direction. So you're doing no work.
So E of 1 is what? Minus 13.
If you're going in the x direction, your cosine 0 is going to equal to 1. From there, you actually do work. So,
2 is going to equal what? Minus 13.6 divided by what? 2, right? 2 squared, yeah, which is going to be 4.
the only part of the force
How much? Do I have a calculator?
that does work
4, yeah. Minus 3.4
is a component
Yeah, that's correct. So E3
that
equals
lies
13.6 divided by 9.
with
You get minus 1.5
the
EV.
direction of this placement. That's exactly
So what do those numbers mean?
why we have
E1 minus 13.6, E2
Cosine.
minus 3.4, E3 minus
Down.
1.15.
cosine theta.
So basically, let me go ahead and draw this down.
And also, the opposite is true. The only component of the force
What was the first one you won?
that
13.6.
lie
What was the second one?
perpendicular
What was the third
to
one?
the direction
Minus 1.15.
of
So
motion
you notice is that the first one's what? Minus 13.6, right? The second one is like minus 3.4.
does
It's closer and closer, right?
not
So let's say if this is
do
0.
any.
Here's the other one.
Work.
5, 8, 60, 70, 88. It like gets
So
closer
when
and
we
closer
have
and
our
closer
force
here, right? You with me?
going
So,
and we're going in a force displacement as in my previous example. Let me just go ahead and put this. This is going to be your Fy, Fx. Fx component, which is your F cosine theta, again, your cosine 90 is going to equal to 0, and your cosine 0 degrees is going to equal to 1. So, with this being F sine theta,
You?
this component does not
I was
do
calling him the
work.
Mr. Eli.
because it's going to go to 0.
And regardless,
Keep
you get
going
the wrong
up
number.
in a 90-degree angle. So we said if we go on with the direction of displacement, in this case, let's say if we go at a 0, we're going to get a 1. So where we said your work was FD cosine. Let me go write this down. FD cosine theta. Now we have our theta equals 0 degrees. That means our cosine 0 is going to equal to 1. So basically this little fella right now over here is going to go to 1. So basically your work is going to equal to F multiplied by D.
So basically you get
but what is F?
one that's
F
down the 13.6 level, right?
Is
because this would
the
this
force.
Like, right?
What is
you get the
the
nucleus,
definition of the force? Well, according to Newton's second
first
law,
level, second energy
your
level,
force
third.
equals your mass times
So basically this
your
is
acceleration.
R1.
So we can actually substitute that back in our work equation. So your work
R3, right?
is going to equal to your mass times your acceleration times your distance. That is why it's very important to
That electron might be coming this way,
take a vacation
coming this way,
from work, because too much work
this way, right?
will make you mad.
Until he goes. So
Your mass times acceleration times your distance. Your distance goes up, you're going to have too much work. Your acceleration goes up, your work goes up.
Go from
Your mass goes up,
level,
your work is going to go up.
third
So too much work is going to make you mad.
13.6
And let me go ahead.
plus
and,
1.5.
write it.
Oh, sorry. Minus 1.5 plus that. Plus 13.6.
This one.
It's going to be what? 12.09 eV.
Now,
This one going to first energy level. What do you get?
getting the work,
Minus 3.4.
which is your force times your distance, and in terms of units,
EVs.
your unit for force is your
So
Newton.
the energy is quantized using Bohr-Malone.
I'm going to give it a
and
big
you
letter
cannot-
N. Your unit for your distance is your meter.
of
Your
energy.
displacement is meter, and I'm going to give it a little m. So what would be the unit for the work? Well, it's going to be your Newton meters. And if you remember, what is a Newton?
So, and what you notice that the
For our
energy
previous
is
chapter,
what?
when we defined it,
Negative,
we
right?
had the Newton.
They go from not from positive to
Defined
0,
as-
negative to 0, which makes sense, right? Because you don't want to go bigger, right, from 0 to whatever.
Kilogram
So energy
meters per second squared. So we can actually substitute that in
And
here.
in
So
this
this would
case,
be
each
kilogram meters
is
per second
the
squared.
highest.
And this, ladies and gentlemen, would equal to
Energy
something called, let me go ahead and draw an arrows over here, joule. And we give it a big letter.
No, from 3 4. How much you need from 3 to
J.
4? But you got the.
So
the
basically-
electron is going over here in the first orbit. That's why I'm doing like this, right?
Your
I'm
work,
doing like well, you know
what we're
how
saying
4
is that your
whatever
work
4 is. E4 in this case is going to be what? Minus 13.6 divided by what? 16. Whatever that number
is
closer to
the
0.
amount
How much is it? Do it. Just
of joules
I don't have that. 13.6 divided by 16.
of energy given to an
Yeah, see,
object.
it's like really 0.85 is getting closer to 0, right? That means your
And
5, which is 13.6 divided by 25, is going to be like 0 point something, really smaller. You see what I'm saying?
So basically,
So, what that, E4? if you
your
go from
unit
E2 to E4,
for work.
Minus 3.6 plus 0.85,
Down,
so
your unit for
2.7,
work.
I think. The energy level. Right? Yeah, if you go from the second one to the 0.85 that you just said,
is your joules,
this is closest
which is a name in honor of James Prescott
0.
joules.
R3 is no, R3 is not 13.6. R3
Now,
is not
one thing I always
R1.
get asked, when is
E3
the work
is
is positive
13.6 divided by
and when
9.
is it a negative?
Remember? Here's E3.
Well, I would like to get to think of work.
The closest
as
one we
giving
have
a
right now for this
present
example is E3.
to my girlfriend. So let's say
See what I'm
this
saying?
is my beautiful girlfriend right now over here.
The first one, yes, exactly. Actually,
That's her leg.
if you really want to draw it, let me just draw it. This is what it's really
And
going to look like.
here's
Here's your first one.
lucky me,
Here's your first one.
smiling.
Here's your second.
And I'm gonna give her
Here's your third.
a gift. And I'm gonna put a bow on this gift.
There.
This gift is called energy.
Yeah, and then you know you go in. The more you go, the closer you get to 0. You see what I'm saying? And that's your 0 energy level. That's where the electron going to break free.
And
make sense?
in this case,
So
I am
this
gonna
is
be
this one. Look,
deforced.
this one, the first one is minus 13.6.
So,
and let's say this is the 0
the
EV.
work
So from
is
here to
positive
here, it'd be 13.6 EVs.
when the force
13.6.
is giving away
1.5, yeah, exactly. Take it out.
Energy.
Right? If it's on energy level 3, you see what I'm saying? That's why I said this. Like you're gonna go from here to here, over here, over here, right?
and your work, and let me get a different color for that one. Your work is negative.
Mm-hmm. Yeah.
When the force
Mhm.
is
No, exactly. You cannot
Take
have
it.
it like over here. You cannot have it over here. You cannot have it. It has to be
And,
on the energy level itself.
we-
So on 13.6, 3.4, 1.5.
so
you know what
when
I'm
I
saying?
go
Et
get
cetera.
my girlfriend
You get closer and closer. Like I said, E4 is
the gift
0.085.
of energy,
E5 is going to be what?
here you go.
Go 13.6 divided by.
She is
25.
positive. She is happy. She's getting energy.
Divided by 25.
That means the work I'm doing is
440.
positive.
See what I'm saying? You're getting
If-
closer to 0.
I take it away from her,
So 0.
that's when you get a negative response,
E3.
and your work
In this example,
is negative. So, and again,
to 0. E1, E2, E3. Let me just write this down, maybe.
this has to be as the same direction as the displacement.
No. E1, E2. Is that better? E3.
And
Now,
this is gonna
when,
be,
I mean, think about it. When you're R, this equals to infinity.
opposite
Let's say your radius is infinity.
from
Okay?
the
Remember, R is what? N squared R1, right?
direction
If your radius is
of
infinity, right?
this.
That means your
Placement.
potential energy is going to equal to what? 0. And your kinetic energy is going to equal to approach to
Now,
what? To 0. That means your total energy is
At
gonna
this
equal to
point,
what?
we said earlier that we're gonna assume, we assume
So-
that cosine 0 is gonna equal to 1. That means, we're assuming that all the forces lie along the direction of displacement, so we're just gonna make it easier. So, let me go ahead and write this down. Let's assume
So positively charged nucleus,
that all the forces
attract
lie along
the negative charged electrons. Now the electron is orbiting
along the direction of the displacement.
R1.
Which means that our work, which is
R1
FD
is gonna
cosine theta, Again, that means your theta is going to equal to 0 degrees.
R1, that means what? N equals what? 1,
I'm
right?
gonna take that better.
Which means your E1 equals minus 13.6 EV.
Which is going to result in your
Now, if you
cosine
add
of 0 is going to equal to
enough
1.
energy,
So that means your work equals your
Because-
force minus distance, and we've seen that equals to MAD.
the electron,
So your work makes you, too much work makes you mad.
the first,
Well, let's take a look at
Energy
this
level.
AD over here, for instance. If you remember from Newton's equation, what do we have? We have the final velocity square is going to equal to your initial velocity square plus 2ax. Let me go ahead. Label this final velocity initial velocity. This is your acceleration.
yeah. The
And
electron is
x
orbiting R1.
is your displacement.
It's going around R1, right? Yeah,
Your distance.
it's orbiting.
And just to make it easier, I'm just gonna make x equals to d for the distance traveled. So
Elevate.
basically, your final velocity square is gonna equal your initial velocity square plus, and let me actually go ahead and write I on this one so it'll be just easier. So vi squared plus 2a
Now, if you provide
d.
enough
Solving
change,
for this little
Yeah.
fella, AD, this is going to result to
Now,
your V
if
final square minus your V
provide-
initial square divided by 2. Well, we can substitute this little fella over here
the
with
electron,
the work equation.
enough.
So
Energy.
really our work equation is going to equal to your mass times your final velocity square minus your initial velocity square divided by 2, which is going to equal to
Infinite distance.
m over 2 times vf squared minus m vi squared over 2.
Away from the nucleus.
Which, if we remember, that kind of actually looks like a really familiar equation that we used to have, that we actually seen before, which is your kinetic.
Basically, you have no attraction pull.
Energy. And I'm going to give it the letter Ke. And we said the kinetic energy is going to equal to your mv squared over
Force.
2. Well, that means this
Just
first
energy.
term over here, that's going to be your
You
final
have enough energy.
kinetic energy.
Because electron can go
And this
from
term
the
over here,
second
that'd be
to the
your
second side,
initial
to the second energy level. You provide the
kinetic
electron enough energy
energy.
to take it to an infinite distance away from the nucleus. And you'll be free. Right? Where you have no attraction pull or no attraction force.
So basically,
That's
our
where you
work
have the
is
electron.
going to equal to your kinetic energy
Is
final minus your kinetic
free
energy
From
initial, which is going to equal to, you got your final minus your initial, that means it's your delta, it's your difference, and your kinetic energy.
except if you hit it with plutonium, then you get thorium and palladium, and then what? You're gonna have neutrons, and then you're gonna have to split plutonium, and then those neutrons gonna split. Those are gonna do more neutrons. The neutrons gonna make new plutonium, and then you're gonna have a mushroom cloud. But that's a different story. But that's how it happens. Alright? So when the electron is free from the nucleus, what does that mean? It's ionized. That's what you just asked a second ago, right? What's ionization? No, I thought you did.
So your work, so we define the work as your difference in your kinetic energy, which is kinetic energy final minus your kinetic energy initial. Now looking as
So
in a
basically,
different definition, we can define it
from hydrogen.
as,
the hydrogen
and let me go
plus.
get a new one.
So Bohr's model.
basically it's your work is defined as your integration
Provided
from your initial precision x1 to x2. I'll just use 1 and 2
The
for initial and
ionization.
final. From one point to another, force
energy.
dx. And we said the force
for
again
the hydrogen atom.
was your mass times acceleration. So it means that the
Energy.
force is going to equal to integration of ma d of x. Well, and what is m? M is your mass.
And we're gonna stop over here for today. I think that's enough.
And a, in this case,
ADI and energy.
that's your acceleration. What is an acceleration? Well, the acceleration was defined as your dv over your dt is your velocity over your time.
Finishing this
So we can actually substitute this
Thursday.
back in our little integration. So you got your integration from your x1 to x2, x1 to x2, m dv over dt d of x.
Now let's go to the department. And with helping, I'll give.
All right. Well, let's take this little dv for a second. Let me actually get a better color than that. Okay. So you got your dv over dt, and let's go ahead and multiply it by 1. And in specific, let's go multiply by dx over dx. And let's rearrange it a little bit. So what we're going to have? We're going to have dv over d of x times d of x over d of t. Well, we have seen d of x over d of t before, which is your velocity, which is defined as your change in distance over your change in time. So this really is going to equal to, if you actually substitute it in, dv over dt dv of d of x times the velocity v. Well, substituting this back, this is going to equal to your mass, since it's the same, dv over dt, we said is going to be d of x, d of v over d of x, multiplied by the velocity, d of x. And what a coincidence, our d of x's cancel out. So this is going to equal to your integration of your mass times your velocity times your d and v, which solving for this, again, you're going from x initial, x1, to x final, x2, whatever, x1 and x2. So this is going to equal to your mass. You're integrating for v, so it'll be v squared over 2 for your initial, I'm sorry, I made a mistake. It's from v initial to v final. So you're going from v initial 1 to v final 2. I'm just going to go 1 and 2. Which is going to equal to m times whatever that final value squared divided by 2 minus m times your initial value squared divided by 2. And again, this looks like the kinetic equation, which is your mass times velocity squared divided by 2. So here is your kinetic energy final, and we're going to say this is our kinetic energy initial. So This gives us back to the conclusion, using calculus this time, that your work is going to equal to your kinetic energy final minus your kinetic energy initial, which basically your work is going to equal to delta K E. And I do thank you for watching, and I hope you enjoyed it.